In this video, I would like to talk about a few more physical quantities associated with movement, namely speed, distance traveled, and displacement. Alrighty, the speed, distance traveled, and displacement formulas are, fortunately for us, very similar in two-dimensional and three dimensions as they were in one dimensions. In one dimensions, if we had a function f of t, which represented the object's position, then f prime is what gave us the object's velocity. Now, velocity contained information both about the object's speed and the object's direction. If the object was moving forward, then it would be assigned a positive velocity. If the object was moving backward, it would be assigned a negative velocity. Now, if you decided to discard that information about the sign, discard the information about the direction by applying the absolute value to that number, then that would give you just the object's speed. Now, if you took your velocity and you integrated it from some initial time to some final time, then by the fundamental theorem of calculus, the quantity that you would get is the antiderivative of velocity, that is to say position, with the final time plugged in, and the antiderivative with the initial time plugged in. And this difference between the final position and the initial position is what's referred to as displacement. I don't care what you were doing in the middle. All I care about is the difference between where you were at the start and where, at the end of the day, you ended up. So if an object moved forward a little bit, and then moved backward a little bit, and then moved forward a little bit again, the displacement completely ignores all this back and forth motion that's happening in the middle of the journey. The displacement only cares about the difference between the position at the end and the position at the beginning. Now contrast that with what you get if you integrate not the velocity of the object, but if you integrate the speed. If you integrate the speed of the object, the quantity that results is the total distance traveled by the object between time t0 and t1. The total distance traveled does care what the object was doing between the initial time and the final time. If your object moves back and forth, then the total distance traveled will treat all of those movements as being in the positive direction and sum them up. And putting it all together, it will give you the total distance traveled by the object between the initial time and the final time. Now, the formulas in two and three-dimensional space are extremely similar. If you're in two or three-dimensional space and your position is being represented by a vector valued function, then we know that the velocity can be found by taking the first derivative, and the speed can be found by taking the magnitude of the velocity. Now, one of the neat things is that the notation for speed is very similar in one dimensions as it is in two and three dimensions. The tricky thing becomes remembering that there is a difference in the formula for the absolute value of a number and the magnitude of a vector. For the absolute value of a number, all you have to do is change all the signs so that everything is positive. But for the magnitude of a vector, don't forget that this is the thing that asks us to take the square root of all the different components squared and add it together. If you want to figure out what is the displacement of the object, that can be found using a formula that's very similar to what we used before. In one dimensions, it was final position minus initial position. In this case, the displacement would be the vector stretching from the final position of the object to the initial position of the object. And if you calculated the length of that vector, you would be able to figure out how far apart is the initial position from the final position. The length of displacement would be equal to the straight line distance between where you were at the initial time and where you were at the final time. Now finally, if you did not want to find the displacement, if you did not want to find the straight line distance between your initial and final position, if instead you wanted to find your total distance traveled, then once again, that can be found by integrating the speed, integrating the magnitude of your velocity vector. So I want to emphasize this difference between displacement and distance traveled. Displacement does not care at all what was happening between point A and point B, between the initial time and the final time. Displacement only cares about the beginning and the end. However, if you didn't move in a straight line from point A to point B, if your path took you on a slightly different, less direct journey, it is distance traveled that accounts for this entire movement that you have done getting from A to B. Beginning and end, and everything in between. So let's do a quick example. Let's do a calculation. Suppose we have an object whose position is given by this function e to the t, square root 2 times t, e to the minus t. Let's go ahead and calculate the object's speed. So I'm going to start by finding the object's velocity, which is equal to e to the t, this constant multiple square root 2, and negative e to the minus t. The speed would be equal to the length of that, the magnitude of this vector. So the square root of e to the t quantity squared, of root 2 quantity squared, and of negative e to the negative t quantity squared. Let's clean that up. That would be equivalent to e to the 2t plus 2 plus e to the negative 2t. Now I claim that this quantity can be simplified. I'm peeking down here ahead to part C. There's a reason I really want to simplify this speed function. To find the distance traveled, I'm going to need to integrate the speed function. I'm going to need to integrate that between the final time and the initial time. Now imagine integrating this expression that I currently have. As it's presently written, it would be essentially impossible to integrate this because I would need to use u substitution to even make it possible, but I would not be able to bring u substitution fully to fruition with what I have now. Now, the key that I'm going to use here is the following principle from algebra. The principle from algebra that I'm going to use is this one. If you have an a plus b, that quantity, raised to the power 2, if you distribute this and simplify, then that's the same thing as a squared plus 2 times a times b plus b squared. Now what I have looks rather similar to that. Three terms added together. The first term is equivalent to e to the t squared. The last term is equivalent to e to the minus t squared. And the middle term at least has a 2 in it. But if I think of e to the t as a and e to the negative t as b, something interesting becomes apparent about this slot right here next to the 2. If I put an e to the t times e to the negative t in there, if I put an ab in there to try and match the format in this algebra formula, I find that e to the t times e to the minus t, these two multiplied together would just be equal to 1. And therefore, this expression here in this bottom side is truly equal to what I have in my expression. So by acknowledging that my expression is in the format of this algebra formula, I realize that what I have in my expression can be rewritten as a e to the t plus b e to the minus t quantity squared. And therefore my speed is equivalent to the square root of that quantity. Now, if you're feeling a little bit unsure about that, if you're not quite sure that that's valid, you can always do a little check. And you can confirm that if you take e to the t plus e to the minus t and multiply it by itself and simplify that you will truly recover, after simplification, this expression that we have in our original equation under the square root. All that we've done is essentially factor it. Now that we've factored it in this way, we can simplify the speed as e to the t plus e to the minus t. So this formula will give us our speed at any given time. Okay. Now that we have that, I don't see any reason why we shouldn't just do part C now. The distance traveled is equal to the integral of the object's speed, and we just found that the speed was e to the t plus e to the minus t. So let's integrate that from 0 to 1. The antiderivative would be e to the t minus e to the negative t. And if I plug in those values, I get e to the 1 minus e to the negative 1 minus e to the 0 minus negative e to the 0. So all in total, the distance traveled would be equal to e minus e to the minus 1 after simplification. Now scrolling back up, let's contrast that with what we get if we calculate the displacement between the times t equals 0 and t equals 1. Now, the displacement vector between our initial position and our final position, I could get by just plugging t equals 0 into our position function, plugging t equals 1 into our position function, and subtracting the two results. Now if I plug t equals 1 into our position function, then that will become e to the power 1 root 2 times 1 and e to the power minus 1. If I plug t equals 0 into that same expression, then I get 1, I get 0, and I get 1. So our displacement vector would be e minus 1 root 2 and e to the negative 1 minus 1. Now if I found the magnitude of that to find the actual distance between the initial and final positions, all I would need to do is calculate the length of this vector, which would be equal to the square root of the x component, the square root of the y component, the square of the z component, all added together, and calculate the square root. It might be possible to simplify this, I don't know, but I'm not motivated to even try, because I don't have anything that I need to do with this quantity later on in the problem. And since I don't need to use this quantity, I don't feel a need to simplify it. Now, when someone asks you for the displacement, as we did in this particular problem, I find that some folks use the word displacement to refer to this vector, whereas some folks use the word displacement to refer to this length here, the distance between the initial and final positions. So just be on the lookout for that. For example, in the homework, just be on the lookout for what the instructions are telling you to do. If there's any ambiguity at all, feel free to ask, and I will try and clean that up for you. For our final piece of investigation, let's go back to the case of uniform circular motion, which we know can be represented by the following vector-valued function: radius r, cosine of omega t, radius r, sine of omega t. In this situation, let's see if we can figure out a couple of different ways to figure out this object's speed. Now, the cutest way to find the speed, based on what we have just done in the previous couple of formulas, will be to go ahead and find the velocity vector, which would be negative r times omega, sine of omega t, and positive r times omega, cosine of omega t. Now that I have this, all that I need to do is go in and calculate the magnitude of this velocity vector. So to that end, I'm going to take the x component and square that. The y component and square that. And then I'm going to try and simplify. Now applying the exponent properties, what we have here is equal to r squared omega squared, sine squared omega t, and another copy of r squared omega squared, cosine omega t. Therefore, I can factor out an r squared omega squared and leave behind a copy of sine squared of something plus cosine squared of that same something, and that quantity, by the Pythagorean identity, must equal 1. So I have the square root of r squared omega squared. And since both r and omega are positive, the speed must reduce to simply r times omega. So r times omega is the value of the speed of an object moving in a circle as controlled by this particular formula. Just take the radius and multiply it by omega, and that is the speed of your object.